If you want to understand who gets rich in a technological revolution, do not start with the product everyone is talking about. Look for the bottleneck everyone depends on. Most people think the AI boom belongs to companies like Nvidia, OpenAI, and Microsoft. But behind all of them is a company most people have never heard of, a Dutch company that controls one of the most important bottlenecks in modern civilization. ChatGPT's launch captured the world's attention, but the real story began in the server rooms. Training a modern AI model now demands hundreds of billions of parameters, numbers so large they are almost abstract. What grounds them is the physical reality, racks of Nvidia GPUs, each the size of a pizza box, stacked by the thousands inside sprawling data centers. These clusters draw megawatts of power, enough to light up a city block just to train a single model. OpenAI's GPT-4 required hardware so advanced that only a handful of facilities on Earth could host it. Microsoft's cloud division, racing to keep up, poured billions into new infrastructure, filling entire warehouses with the latest accelerator chips. Every breakthrough in AI, every leap in what machines can generate or understand, is matched by a leap in the hunger for compute. The visible brands, Nvidia, OpenAI, Microsoft, sit atop an invisible mountain of silicon and electricity. Each new model, each product launch, pushes hardware to its edge. The race is not just for smarter software, but for more transistors, denser chips, and faster interconnects. The public sees the apps and the headlines, but underneath, the scale of engineering required is almost unfathomable. The question is not just how these companies keep pace, but how the silicon itself keeps up with the demands of artificial intelligence. Lithography sits at the heart of chip making, acting as the master printer that translates abstract circuit designs into physical reality. The process begins with a silicon wafer coated in a thin film of light-sensitive material. Using a mask, beams of light project intricate patterns onto the wafer, fixing the blueprint for billions of transistors in place. Each transistor is a switch, and the smaller these switches become, the more can be packed onto a single chip. This density is not just a matter of scale, it is the main lever for performance and efficiency in modern computing. As feature sizes shrink below 10 nanometers, the rules of the game change. The wavelength of the light used in lithography becomes the limiting factor. Shorter wavelengths allow for finer details, enabling manufacturers to print ever smaller gates and wires. The minimum gate length, set by the sharpness of the lithographic process, directly defines how many transistors fit in a given area and how little energy each operation consumes. When a chip designer moves from a 7 nanometer process to a 5 nanometer one, the result is not just more transistors, but a measurable drop in energy per calculation. This is why the most advanced AI accelerators, from GPUs to custom neural processors, are built on the tightest possible nodes. The path from software ambition to hardware reality runs through the precision of lithography, setting the pace for every leap in artificial intelligence. The bottleneck is not in the algorithm, it is in the ability to print smaller, faster, and more efficient circuits onto silicon. ASML's rise to dominance was anything but accidental. The company's leadership understood early that the path to controlling advanced lithography would be measured in decades, not quarters. Peter Wennink, who would later become chief executive officer, championed a funding model that spread both risk and reward. In 2012, ASML brought together Intel, TSMC, and Samsung into a consortium, pooling over €1 billion for the high-stakes push to make EUV lithography viable. Each partner committed capital upfront and secured early access to the technology, while ASML locked in a pipeline of orders that would justify the enormous research spend. Christophe Fouquet, then leading technology strategy, mapped out a product roadmap that stretched years into the future. He worked closely with Zeiss for optics, Trumpf for lasers, and the world's largest fabs to align development timelines. This meant that every advance in EUV, higher source power, sharper optics, better mask handling, could be commercialized as soon as it was ready, with customers already on board to absorb the risk. On the operations side, Martin van den Brink drove a transformation that allowed ASML to scale production without sacrificing precision. Tool ramp-up times dropped from 18 months to less than a year, a shift that enabled the company to keep pace as demand for EUV machines accelerated. By building a network of risk-sharing partnerships, exclusive supplier agreements, and co-development deals, ASML engineered a position that no competitor could easily replicate. The monopoly was not a fluke. It was an outcome designed through coordinated, long-horizon bets and a willingness to share both the burden and the upside of innovation. Extreme ultraviolet lithography draws its line in the sand at 13.5 nanometers, a wavelength so short that ordinary glass absorbs it, and even a fingerprint can ruin a mirror. To generate this light, a high-powered Trumpf laser fires at droplets of molten tin, creating a plasma that emits EUV photons. The laser system alone is the result of years of joint engineering, and there is no off-the-shelf alternative. Every EUV tool relies on this single-source partnership. From there, the light must be shaped and focused. Zeiss in Germany produces the only mirrors smooth enough for the job. Each one is a multi-layer stack of molybdenum and silicon, polished to less than half a nanometer of surface error. So precise that the entire set of mirrors in a single machine is worth more than a private jet. The optical path is so sensitive that even a stray molecule of water can degrade performance. No other optics company has managed to reach this level of precision, and the process is protected by patents and trade secrets. The result is a machine that costs up to $380 million per unit and draws 1.5 megawatts of electricity, more than some small factories. The mirrors alone take more than a year to produce, and the supply chain is locked by exclusive agreements. Any attempt to copy this ecosystem would demand not just capital, but a decade of patient development and the cooperation of companies who have no incentive to help a rival. Physics, not just business, sets the boundaries. The tolerances are so tight that a single cracked mirror or a misaligned laser module can halt production for weeks. The moat around EUV is built from the fundamental limits of light, the scarcity of suppliers, and the sheer complexity of the system. This is monopoly enforced by the laws of nature as much as by economics. In the early 2020s, a new form of power began to crystallize around the tools that make advanced chips possible. ASML's extreme ultraviolet systems, once the domain of engineers and physicists, became the subject of export licenses and diplomatic negotiations. The United States pressed the Dutch government to restrict shipments of the latest EUV machines to China, citing national security concerns. Each shipment now requires approval, turning what was once a commercial transaction into a geopolitical event. At the center of this tension sits Taiwan. TSMC, operating out of Hsinchu and Taichung, produces nearly 3/4 of the world's sub-5 nanometer wafers. These are the building blocks for every leading-edge AI accelerator, from Nvidia's H100 to Apple's latest system on chips. The concentration is extreme. A single island, home to a handful of fabs, holds the keys to the world's most advanced silicon. Any disruption, whether political, natural, or regulatory, can ripple outward, threatening the AI ambitions of entire nations. The tools themselves have become bargaining chips, shaping alliances and defining the boundaries of technological influence. Railroads once dictated where goods could flow. shaping entire economies with the placement of a single track. Oil pipelines turned the movement of fuel into a private toll road, with Standard Oil setting prices not just for oil, but for everything that depended on it. In the 20th century, control shifted to the fiber optic cables and undersea routes that carried the world's information, and later to the cloud platforms that now anchor the digital economy. Each time, the companies that owned the bottleneck, whether steel rails, pipelines, backbone cables, or server farms, exerted quiet power over the visible giants riding above them. Today's semiconductor supply chain fits the same pattern. The breakthrough AI models and the brands that headline their success are only possible because of a single, irreplaceable layer beneath them. Just as the Panama Canal once set the pace of global trade, the wavelength of EUV light now sets the pace of technological progress. The monopoly is not in the product you buy, but in the gate that every competitor must pass through. The lesson repeats. In each era, the deepest leverage belongs to those who control the infrastructure everyone else must use. Right now, the most advanced artificial intelligence still depends on a single, unseen gatekeeper. As demand for AI accelerates, the leverage held by those who control the bottleneck only grows. The next chapter of innovation and power will be shaped not by code, but by who owns the keys beneath it.